Solving circuits using Fourier transforms is a lot like phasors, in that resistors are redrawn as resistors, capacitors are redrawn as 1 over j omega c reactances, and the reactance of an inductor is drawn as j omega L, just like phasors. They are, however, a lot like Laplace methods, in that first you will change the circuit, my abbreviation for circuit CKT, into the frequency domain, and then you will solve for the output y of omega, and then use the inverse transform to find the output in the time domain. When you do this, remember you can change your j omega into an s to make the algebra a lot easier, and that includes minus omega squared gets replaced by s squared. Also from last class, when you find the inverse transform, remember to make sure that your fraction is a proper fraction. And if it isn't, do long division to make it so. And last, you may need to do partial fraction decomposition to get that inverse Fourier transform. But a third point is that Fourier transforms are better than either phasor analysis or Laplace transforms. It can handle U of t functions, unlike phasors. It can handle cosine of t functions, unlike Laplace transforms, but like phasors can. And last, it can handle double-sided functions, like e to the minus absolute value of t. Great, so let's give a quick example. Let's say you've got a circuit in the time domain, and it's given a input function that looks like this. It goes from minus 5 volts, and it pops up to plus 5 volts. And that is the voltage that's given to this circuit. It has a 1 Henry inductor and a 4 ohm resistor. And the question is, find that voltage across the resistor. So the steps are already given here on the left for the Laplace transform. The first is to change the circuit into the frequency domain. To do that, we need to find out what our voltage is in the frequency domain. In the time domain, it's minus 5 plus 10 u of t. This way, it starts out at minus 5. It's minus 5 everywhere, but for time greater than 0, it's 10 more than negative 5, which makes it plus 5. So now we need to transform that into the omega domain, into the frequency domain. Here's a snippet of the transform tables we used last class, and so we can read out that that minus 5, along with the linearity property, is a unity, which goes to minus 5 times 2 pi, or minus 10 pi delta of omega. And to that, we'll have to add our 10 u of t. So that's 10, and let's see, that's going to be 10 times everything. So that's 10 pi sample of t plus 10 over j omega. Well, that's rather nice. You can see that these two things cancel, and so our overall transform of our input is just 10 over j omega. So let's redraw the circuit in the frequency domain. The source becomes a 10 over j omega voltage source. Our inductor becomes a j omega reactance. The resistor stays 4 ohms. And we're still trying to find out this voltage across the resistor that I'm going to draw as clearly a capital V right now, since we're in the frequency domain. So this is a voltage divider, and by the properties of a voltage divider, it's equal to the input voltage and then times the numerator, the voltage across the component you're trying to find, divided by the total impedance. Now, using the trick of substituting s for j omegas and s squared for minus omega squared, we can say that's like 40 over s times 4 plus s. So now we have to do our inverse Fourier transform to bring it back in the time domain. I can see that this is a proper fraction, but I need to do partial fraction decomposition first. So that gives me something over s plus something over 4 plus s. Using the cover-up method, I cover up this s. The root of this s is 0. So now plugging in 0 for the remainder of this equation, I get 40 over 4, which is 10. Now we'll cover up the other side. The root here is at s minus 4. So plugging in s minus 4 into this gives us 40 over minus 4, which is minus 10. I'm going to write this on the left-hand side just to save a little room, using the notation of Fourier transforms, which use the j omegas. All right, let's call up our Fourier transform table and see how we can convert this into something that appears in our table. Let's look for something that has a j omega in the denominator. The only place that we see the j omega in the denominator is right here. So using the method we've used from the start of the semester, let's write down not what we actually have, but what we wish we had. I'm going to flip the order of the table. So I'm writing the 1 over j omega first. Now, if we were given this, instead of this upper part, if we were given this lower part, it would read directly on this table. What do we need to do to this lower part to make it look like this middle part? Well, if we multiplied it by 10, we'd have this first part done. But the problem is then we'd have 10 pi unit sample of omega too much. So let's subtract 10 pi unit sample of omega. And now this is mathematically identical to this. And this intersection is exactly equal to this entry on the table. So we can convert it. The problem is now we've got a minus 10 pi unit sample of omega, but that looks a lot like this. So let's convert the form again. Pretend that we don't have minus 10 pi unit sample of omega. Pretend that we have minus 2 pi unit sample of omega. And then this perfectly maps onto the table. And all we need to do to make this equal to what we're actually given is to multiply it by 5. So we know that everything we have underlined in yellow is the same as everything we have underlined in yellow above it, which is the same thing as the short first part that we have underlined in yellow. But the difference is that all the parts we have underlined in yellow, specifically the green and the blue, are in the table just multiplied by constants. We still need to do something with the second part, this 10 over 4 plus j omega. Looking in the table, that looks very similar to this section. So we can rewrite it like that. 1 over 4 plus j omega, all multiplied by 10. And now we can identify that this is the same thing as what we've underlined in gray over here. So we're finally in a position to write our entire transform, which is v of t is equal to 10 times u of t minus 5 times just 5 minus 10 times e to the minus 4t u of t. And that's entirely correct. A more compact way of writing that same thing would be to say it's equal to 10, 1 minus e to the minus 4t u of t minus 5. Now you could have derived that same result using EE223 techniques, identifying this as being a first order circuit, but with a minus 5 volt offset. So you could have added 5 volts to the entire thing, which would make it look like a pure step at 0 going up to 10, and then subtracting that 5 once done. But using Fourier transforms lets you do it all in one step.